Okay, welcome everyone to my continuation of what is algebraic graph theory. Today, a change of topic. And I'm trying to kind of motivate the change of topic in a slightly funny way, well, whatever funny is. Well, let's see. Today will be kind of a little bit relaxing because I want to motivate this idea of graph polynomials, which is kind of exactly the different type of approach to graph theory than what we have seen so far, which I would like to call the spectral approach. So easy problems, not hard problems. So the spectral approach, if you want, is mostly about hard problems, and we get approximate solutions for hard problems. And graph polynomials is kind of the opposite. There are some easy problems, and we get nice, concise kind of solutions for easy problems using polynomials. Is kind of a nice approach, and I would like to motivate that today. Again, a little bit relaxing and easy. I hope it's always relaxing and easy, but you will see. So here comes why it is relaxing and easy, because I would like to use this XKCD very questionable illustration, which I think still works very well. So let's say we're talking about fruits. Why not? In the end, fruits will be mass ideas or mass statements, whatever. And a fruit can be tasty or untasty, ignoring the fact that that will depend on the person, whether you like a fruit or not. And it could be easy to get or difficult to get. Again, let's ignore the kind of technicalities here with what is subjective, what is objective. Anyway, oversimplified, we would like to divide graph theory into easy and difficult problems and in tasty and untasty problems. I'll give you some examples as we go. Right, so a peach, apparently to the author of XKCD, is easy to get and tasty. Why apparently the grapefruit is not very popular, it's difficult to get and untasty. If you would like to ask me, I just hate all of them. For me, they're all untasty, but I can still agree that the pineapple is certainly more difficult to get than a red apple, right? So that's kind of this idea of this two-dimensional grid. I hope that works for you. Again, ignore that some definitely different people have different tastes. What is easy, what is difficult, what is tasty, what is untasty. But I really just want to apply this to graph theory because why not? We can. So let's do it. Okay, so spectral approach is essentially dividing this picture into the middle. So spectral approach is here. It's concerned about difficult problems, right? And that's what we have seen so far. And what we usually get is it's designed to tackle difficult problems kind of approximately. We get bounds or something that is true in the limit or something like that, right? So it gives some bounds or asymptotics or whatever. And for example, we have seen that this clustering, which I liked a lot, and that's actually a difficult problem, but somehow the result wasn't maybe not so nice because it was more like a hand-wavy algorithm or heuristic type thing, so I put it here. The counting pass is the first we have seen, really efficient, Perron-Frobenius theory, Perron-Frobenius eigenvalue, very tasty in my opinion, but maybe not so super difficult to get. The Hamiltonian condition, whether a graph is Hamiltonian, extremely difficult to get. And the result was kind of nice in the end. There was, again, some bounded approximation stuff going on. So maybe it wasn't super tasty, but it was kind of nice. I hope you get the kind of a picture I want to draw here. Obviously, where those problems sit exactly depends very much on the speaker, right? So again, the XKCD also apparently likes peaches. I hate peaches. There you go. It depends on the speaker. But honestly, I hate everything anyway, so that doesn't really matter. Anyway, so I hope you get kind of the point here is really the spectral approach gives approximate solutions for difficult problems. And kind of the opposite is a polynomial approach, which we are going to discuss from this video onward, which gives kind of exact solutions for easy problems. And not just exact solutions, I would also claim it gives, or this color works really horrible here, so let's make it black. It also gives kind of nice explanations for something. Here is an example which we will see, for example. I think something that is relatively easy but also very tasty. It's like counting the number of forests in a graph. That's not so really difficult, but it turns out that there's just a polynomial, which we will call TG in a second. Well, we already call it TG here. So it's a TAT polynomial. It has two variables, x and y. It's a polynomial in two variables, and if you evaluate it at 2 and 1, you get some number, and that's the number of forests. And I think that's a pretty tasty, actually a pretty tasty statement. So that's kind of how the polynomial approach works. You have a statement, a theorem, or a fact that is not difficult to get, like counting number of forests, but you can beautifully encode this into evaluating polynomials at points. Something very easy, you could just evaluate at a random number, so not 2 and 1, but whatever pi squared and e to the square root of 2, something like that, and you get a random point. It doesn't mean anything, so that's a rather untasty problem. Right now, we don't have many things to fill in here, but because we'll start from here on, but I hope you get the point that there might be some really nice statements, some very surprising, difficult looking problems that are actually easy to compute by using a polynomial, or there could be something boring, of course. But the difference is kind of polynomials give a sweet and short explanation, short and sweet explanation for kind of easy facts about graphs, while on the other hand, the spectral approach gives approximate solutions for usually way more difficult problems, right? Say it again, approximate solutions for difficult problems, or exact and sweet and short solutions for easy problems. That's kind of the difference between the polynomial approach and the spectral approach, that we will see the polynomial approach from now onwards, at least for a couple of videos. It's really, really beautiful. So here, for example, there is this polynomial, which I already mentioned, and it will appear later on. It's called the TAT polynomial. It's associated to a graph G, such that if you evaluate it at certain points, like 1, 1 is the number of spanning forests, 1, 2 is the number of spanning subgraphs, and so on. And this is kind of really great, because computing the polynomial is somewhat easy, and evaluating the polynomial is also somewhat easy. So those problems that actually show up as evaluate TAT polynomial at whatever point are easy by definition, if you want. And this was exactly my picture I had here. So I just put the first one somewhere on this little XKCD kind of tasty, untasty grid, graph, whatever it's called, plane, the tasty, easy plane. And that's the whole idea here of so this type of graph theory. And that's pretty beautiful. So because the polynomial itself counts interesting graph theoretical objects. So again, I stay with my TAT polynomial, which we'll see in a later video in more details. But the polynomial itself is also absolutely fabulous. It generalizes many things like the Potts model, which is really, really exciting. But it also comes with beautiful formulas and beautiful pictures. Like here, you can compute it recursively. So what I'm trying to say is the polynomial approach solves problems in graph theory in a nice way, but the objects you get, the polynomials, are interesting in their own right. And that's what we're going to explore in the future videos. Hopefully you liked my playful approach to kind of explaining what the difference between spectral, my playful approach to explaining what the difference between spectral and graph polynomial, kind of the theory of graph polynomials is with respect to, well, what you want to know about graphs. It's really this idea of easy problems can be solved in a much better way than hard problems, and you need different approaches. And well, whatever you want, right? Hard problems are kind of more important because they're hard problems, but they have a slightly awful solution in some sense, right? You only get approximations or something, while easy problems are less attractive because they're easy in some sense, but they get really nice solutions. So we have this nice division of the fruit plane, we call it the fruit plane, of the fruit plane into easy and hard problems attacked by spectral theory and polynomials. Anyway, I hope you enjoyed this video, and I also hope to see you next time.